Some of the functions we deal with have breaks or jumps in them. So we're going to look at two different types of functions that have these breaks or jumps. One of these is called the greatest integer function. And this one here has a special symbol. It looks like brackets, except it's a double bracket. And it's actually connected like that. That's a greatest integer function symbol. So kind of like brackets, but double. What this does is it returns the largest integer less than or equal to x. So if you're looking at a chart like this, what's the largest integer less than or equal to x? Meaning we want the 1. For 1.5, the largest integer, well, 0.5 does not take us up to an integer, so the largest integer that we could get out of this would still be 1. Even with 1.99, it's close to 2 on the number line, but it's not quite at 2, so the largest integer we get out of this is still 1. This is kind of different for us. We're used to thinking about rounding up, but with this function, we want to think about rounding down. Because again, we're asking, how many complete sets do I have? If I'm counting towards dollars or money, how many actual complete dollars do I have in my possession? I technically only have $1 and a bunch of change. For this one here, we'd say it's 2, 2.4, the large integer still 2, 2.99, still 2. You only have a complete integers up to 2. And then you jump to 3. So that sounds a little different to us. The graph then is another interesting picture. To graph this, we want to go ahead and go to your math key. Then you're going to go sideways to number. And then you're going to go int. So math, number, down here int. You need to make sure that you're in your y equals for this. So y equals math, num, int, x. And it looks like this staircase or a bunch of steps because you're jumping. See, we're going to have 1s, then 2s, and then a 3s. So looking at our graph right here even, we have no integers from 0 to 1. We're still in the decimals. So we're still on the 0 line, if you will. Then we're going to jump up to the 1 line. And then from 1.5, 1.9, even though those are right here, your largest integer is still 1. As soon as you hit 2, you jumped up all the way for 2.4 and 2.99. 3, you're going to jump up. So here's our staircase. But the graphing calculator doesn't even give us the whole picture. We want to say what's happening at the ends here. We know that from a vertical line test, you cannot have places that overlap. So this point and this point cannot both be used by this function at the same time. So in order to say this is a function, we're going to say here at 1.99, for example. So 1.99, I'm still at 1. At 1.99999, I'm still at 1. But as soon as I hit 2, I've jumped up. We are using that. This one gets super close to 2, but never touches, because as soon as you actually hit an x value of 2, you're now suddenly on the next step. For 2, we're at 2.12, 2.42, 2.82, 2.92, 2.99999, still at 2. As soon as we hit 3, though, we've jumped up. So this one includes the left-hand side of the steps, but open circles on the others. So fill that in. That's important for us to know for these graphs. And again, this is because we're rounding down with this function that you're going to include the lower value but not include the higher value as we're rounding down. This greatest integer function is also an example of what we call a piecewise function. For a piecewise function, this is where you have different pieces, that's why I call it piecewise, that you're graphing at the same time. The main idea here is that each equation that we have is only valid for a certain interval of x values. So this is part of our equation, but it's only good for this section of our graph. We're going to use open and closed circles again to indicate where things are included or not included. Again, as we used up before, remember that a closed circle means included and an open circle means not included. So for x plus 1, that's a linear function. It's a line that has a slope of 1 in front and it has a y-intercept of 1. So y-intercept of 1, slope of 1 would give us something like this. I'm doing it in dots right now to show that it's not my final answer, but some sort of linear function. It's only good where x is less than 3. So on my graph, 1, 2, 3, as long as I have an x value on the left-hand side of this pen, then this line is good to go. So I want to say, coming down here, that's part of my function. It's not valid or it's not good or it doesn't work as soon as I plug in an x that's greater than 3. Now, at the actual 3 point here, do I include this? No, because it's just less than. So an open circle here indicates that that straight line comes really, really close to this point, but does not actually include it. The next piece of my function is this -2 part. This is a constant function, so at -2, that would be the line that comes through here. This is good as long as x is greater than 3. So as soon as I have x is 3, I'm going to have something at -2. 3.1, it's going to be at 2. 3.5, it's going to be at 2. In fact, all the way out, I'm going to be at a y value or a function output of -2. The important thing for us to remember with a piecewise function is that you're only using one piece at a time. So again, with this vertical line test, I'm only touching one function at a time. Even as soon as I hit 3, there's an open circle here at 3, so I'm not using this top function. And there's a closed circle here, I'm only using the bottom function. And then again, I'm still only using one function at a time. Something else with the piecewise function then, if I was to say evaluate f of 5, I do not plug it in to both pieces. I can only use one piece. The question is which piece? So I look at, well, if this is my x value in here, which piece is valid? X less than 3? Is 5 less than 3? No, it's not. So I'm not going to use the top piece. X is greater than or equal to 3. 5 is greater than or equal to 3. Yes, it is. So that's the piece I'm going to use. That means that f of 5 would be -2, and then there's nothing to plug in. That's it. Look at your graph. At 1, 2, 3, 4, 5, you're at -2, that point. This is the description of the input of 5, output -2. Let's do another one really quick. Let's say you had 0. F of 0, is 0 less than 3? Yes. So we'll say that this is 0 plus 1 or 1. At 0 on your graph, you're at a height of 1. 0, 1. That's your point. You do not plug this into both pieces. You only use one piece, and you check the restrictions on the back to see which piece you use.